Howdy! Chapter 18, Harmonic Motion. This chapter is different from all the previous chapters. We spent the semester up to this point developing the laws of mechanics. Starting with Newton's laws, we derived the laws of conservation of energy, momentum, and angular momentum, and hopefully we know how they were derived. In this chapter, we do not do anything so ambitious, but instead study the simple system of a mass on a spring. We will not derive any new law, but we'll see that we can solve for the motion of the mass even when there is a type of friction present and when the motion is driven by some external force. There are good reasons for spending a lot of time on this system. First, it is a good place to apply a lot of what we have learned. Second, we have to learn some new mathematics, always a pleasure. Third, we will find exactly the same mathematics when we study circuits next semester, and it is good to learn the math for this simple mechanical system. Most important is that we are surrounded by systems that behave in some situations just like the mass on a spring. We will be able to show that such systems display what is called a resonance. This behavior can lead to useful applications or catastrophic events, so it is something that every engineer needs to know about. To convince yourself of the importance of understanding oscillating systems, please go to any search engine and have a look at the bridge over the Tacoma Narrows. Not understanding resonances can have serious consequences. We start by considering the simplest system, a small block attached to a spring. We can find the potential energy function for the force of the spring, or use the work energy theorem to relate the block's position to its velocity. If we want to know where the block will be at any time, we have a problem, because t, the time, does not appear in the work energy theorem. What we are led to is a differential equation which relates a function and its derivatives. You will ultimately take at least one full semester of a math course devoted to solving such equations. Here we take the simple approach of just guessing the solution. After a while, this guessing procedure should not be mysterious. You will need to know how to show that a good guess does solve the differential equation if a certain constant is properly chosen. You should not memorize the answer because the same procedure can be followed for all kinds of systems, not just a mass on a spring. You will also learn that the solution always gives you the freedom to specify what are called initial conditions. For a mass on a spring, that means you must have a solution that works no matter where you start the block and how fast it is going when you start it. We then add a friction-like force which resists the motion and is proportional to the block's velocity. The addition of this viscous drag force leads to an equation we can still solve by an educated guess. The solution describes an oscillation of decreasing amplitude called damped harmonic motion. This is also a very common occurrence in many systems. Finally, we add a driving term of a peculiar form which has a number of advantages. First, we can still solve it the same way. Second, it leads to the critically important result called resonance. Third, it is the same equation that will be commonly encountered when considering most electrical circuits. Having met the mathematics in this simple mechanical system will pay big dividends. There are many examples of oscillating systems that are not just a mass on a spring, but the easiest one to understand is a simple mass on a spring, if we especially ignore gravity. If we were to plot y as a function of time, we would find that it looks like a sine or a cosine function. By isolating the body, writing down Newton's laws, we will end up with an equation. We can all guess the answer to the equation and very well describe the motion. As we might see, as this oscillation goes on, the amplitude is getting smaller and smaller because the mass is actually fighting its way through a liquid, the air, giving up some of its energy. This is really damped harmonic motion. You may have a mass on a string instead of a mass on a spring, and the motion will be just about the same, just a simple pendulum. And if we use Newton's law, best to write torque equals dl dt for this system. We can describe this oscillation just as well. Another example is called a physical pendulum, where instead of a point mass, we have some extended object, but this can also be set into oscillation. And using torque equals dl dt, we can describe even the motion of a ruler. The final point has to do with a resonance, where if we take a mass on a spring and apply a driving force to it, the amplitude of the oscillation of the mass will depend critically on the frequency with which I move my hand up and down, forcing the spring to exert a force on the mass. If I move very slowly, nothing significant happens. If I go very fast, it just sort of quivers. But if you find the natural frequency of a system and then drive it at the natural frequency, you get a large amplitude oscillation. This is called a resonance. It can be extremely useful, and it can be hazardous to your health. Summary. Newton's law is applied to a mass on a spring, resulting in a differential equation for the mass's position. This equation can be solved by guessing. The solution contains two types of constants. One must have a certain value, or the solution does not satisfy Newton's law. The other type allows you to specify the initial values of the mass's position and velocity. The same procedure can be applied to many similar systems, and one can also solve the equations when viscous drag and a driving force are added. The phenomenon called resonance will always occur in such systems. Gig 'em.